Okay. Yeah. Hello, everybody. So, okay. So we continue. So let me just remind you briefly what I did last time. So we were in this function field setting, and I tried to explain how to, starting from some irreducible Galois representation, how to, which is unramified everywhere, how to attach to this an automorphic form in the case of GLF. The idea of the construction was we constructed this function f prime sigma, which was left invariant by the mirabolic subgroup. We wanted to check that it's invariant by the full GLN of f. F is our function field. And I said that it's hard to do it directly, and the way to do it is to do it geometrically by geometrizing via this fifth function dictionary the construction of f prime sigma. Unfortunately, I did not have time to explain how this geometrization works precisely. So this using the L-adic Fourier transform. So I probably come back to that at the end of my lectures. But the claim for this series of lectures is that this parallel story exists in the local setting, so and has interesting applications in the local Langlands program. But to explain this, we need to leave the world of usual algebraic geometry and enter the world of periodic geometry. And so what I want to, so this will take us some time. And what I want to do today is to give some kind of brief introduction to adic spaces. And maybe if I have enough time, define what the far content curve is. And then in the next weeks, we will study the geometry of the subject and properties of vector bundles, coherent shift on these curves in more detail. So today it's mostly about adic spaces, and of course we have to be very sketchy, so probably a bit unsatisfying, but I will try to do my best. So, okay, so the idea is this is a theory which is due to Huber. We want to do geometry like study manifolds, varieties over periodic fields like QP, or the field of, if you like, positive characteristics, the field of Laurent series over a finite field FQ. If you try to do like you would do in topology or differential geometry, like define some kind of naive analog of manifolds in the periodic setting, you quickly run into the issue that the topology on the periodic field is non-Archimedean topology is totally disconnected. So connected components are just points, and so gluing functions is too easy. But so it's better to take the same point of view as in algebraic geometry and try to define this geometric object as locally ring. And this is what Tate was the first to do, and then later on, Berkovich improved the theory, and a bit later, Huber provided what is so far the most general formalism, and this is the one I want to focus on. So, idea is we will define a certain class of topological rings, and to them we will be able to associate geometric objects, exactly like in algebraic geometry. We start with permutative rings and we construct a spec of such a ring. So it's similar here. And so a class of topological rings that we will consider as the following. So the topological ring is said to be a Hooker ring. So let me call this topological ring A. If A admits an open subring A naught, which is I-adic for some finitely generated ideal I. So I-adic means that the topology on this subring A naught is that the power of this ideal they form a basis of neighborhood of the origin. So an element is small if it belongs to a big power of this ideal I. I will give some examples in a moment. But let me continue with the definition first and explain the refinement. So a Hoover ring is said to be a Tate ring if it contains a topologically important, so an element whose sequence of its powers goes to 0, and which is also a unit. By pi. So such an element will be called pseudo-uniformizer. That's a standard terminology. And in fact, one can prove that under this assumption, necessarily, if I choose, so such an A naught is not part of the data. It's just a choice you can make. There are various possible choices of A naught on a given Hoover ring. And these are called rings. So this is a ring of definition. So for Tate rings, in fact, whenever you choose some A naught, in fact, the topology will automatically be just the bar pi adic topology. So the ideal I can be taken to be just the principal ideal generated by bar pi. And A is just what you get by inverting bar pi in from A naught. Okay, and finally, the Hoover or respectively Tate pair is the datum of the pair AA plus, where A is the Hoover ring, respectively Tate ring. And A plus is an open integrally closed subring of A, which is contained in A naught, which is a set by definition, the set of subring of power bounded elements in A. Power bounded means that it's an element such that the sequence of all its positive powers stay bounded. Okay, so the point is, this is exactly the data we will be able to attach a geometric object. So it may be the situation looks a bit different to the situation we know for schemes where we just have a commutative ring, and to this we attach its spec. In adic geometry, you really need to start with such a pair. And the role of A plus is quite crucial, although it's a bit subtle to really understand why it's necessary to have it. So in first approximation, you can maybe just forget about A plus for now and just remember that we start with a Hoover or a Tate ring. And the really important condition about A plus is this one. This is somehow just a technical condition, which can always be unsure.
Saying so A not upper not this is ring power bounded elements.
Yes.
Power bounded was
power bounded means an element X in A is said to be power bounded is the sequence of powers of X stay bounded.
In the
Yeah.
To the attic support, okay.
In the for the I mean my ring A is a topological ring.
Yes, to be Cooper and to be Tate are both properties of the top line.
Yes. Let me now give some examples of just to see which kind of rings we can work with. So, the first example is take just any discrete ring. Will be a Hoover. Right? And in this case, you can just take A naught to be A itself, and I to be here like here. Another example is the case where you take an adic ring. Or finitely generated idea. It's also Hoover. Again, by definition, just by taking A naught to be A, and the ideal my ring is eidetic for some finitely generated idea I, and then the definition. So this is generalization of this case. I mean that the topology is eidetic topology, and in fact, for everything we are doing today, you can always replace the object, all the rings involved by their conditions, and always work with complete objects, because the associated geometric objects won't see the difference between the ring and its condition. So yeah, you are free to assume that everything is complete. So you see, these are examples of Hoover rings, and in particular, the theory we will construct incorporates the theory of schemes and the theory of formal schemes. But it's a big difference with, say, Tate's theory of rigid spaces, which is really about like periodic and analytic objects. Here, we also have a theory which is general enough to also incorporate this kind of examples. And the last class of examples is, so these are not Tate. And as examples of Tate rings, well, you could, for example, look at Clay non-Archimedean field. So it would be, so by this I mean field which is endowed with a non-trivial valuation K, going from K to positive to non-negative real numbers, and defining its topology. So, for example, K can be QT with a periodic norm, or K can be the norm series with the t-adic topology. So you see that here pseudo uniformizer in this example is P. It's topologically nilpotent, but it's also invertible in QP. And here T will be a pseudo uniformizer. In general, you can just choose any element which is non-zero, which has a variation which is strictly between 0 and 1. And this could serve as to the uniformity. And A naught, in this case, A naught can be taken to be, well, just K naught, sorry, A0 can be taken to be K naught, which is just another name for the ring of integers in K. So all elements which have valuations less or equal to 1. Okay. I will come back to what I mean precisely by valuation pretty soon. There is a quite standard but confusing choice of terminology that valuations are something like semi-not, not what you may think valuation. But I will clarify this very soon. Okay, other examples of the text ring. You can take R A, which we take to be usually denoted like this. We should think of as the ring of power series converging on the n-dimensional closed unit ball. I don't have a precise meaning yet, but it will happen soon. And it's by definition, this notation with brackets means that you just take power series, sorry, polynomials in these variables t1 and tn with integral coefficients, and then you take the var pi ID completion, where var pi is so K is supposed to be a field, non-Archimedean field, with a fixed pseudo-uniformizer. So as I said, just any element. And okay, so you take this var pi ID completion and then you invert. So it's just power series in this coordinate t1, tn, such that the coefficients go to 0 for this var pi ID topology when the exponent goes to +. These are, yeah, this is still an example. These are examples of stage. In fact, any Huber ring which lives over a Tate ring is automatically Tate. So a non-Archimedean field is an example of a Tate ring, and any kind of Huber ring I construct over it is automatically Tate. I mean, as you can see from this explicit description, the topology this in here would play the role of A0. The topology on this is the R-periodic topology, and as claimed above, I just reconstruct my ring as what I get by inverting this pseudo-uniformity. Tate rings are the ones that the associated adic spaces will really be objects which behave as one would expect a periodic manifolds to behave. So they will behave quite differently from schemes or formal schemes, as we will see. But still, the formalism encompasses both situations.
So the very basic example is cheap and set to
yes, for example, or this example of a big of four series, Laurent series. Yeah. But geometrically, this is of course more interesting examples because, as I wrote, supposed to see the functions that are defined on the board of dimension. This could be some building blocks. In Tate series, these are really the building blocks. Start with closed boards and then you construct things inside them and closed.
Cake would also be perfect for.
Yes, CP, for example, is another example of a non-Archimedean. Okay, so we want to attach locally ring spaces of such Huber or Tate pairs. And as a first step, we want to get a space, a topological space attached to that. So what are the points of these spaces? It will be spaces of continuous valuations. So, and this is in some sense going back to the perspective of Larity on algebraic geometry. He was using valuations which Groten did not like and that removed from the theory, but in some sense they come back here. So the continuous, so A will be, or in fact can be any topological ring. So a continuous variation is from A to gamma 0, where gamma is the total order abelian group. With the following properties. So first of all, valuation of 0 should be 0, valuation of 1 should be 1. And then we want that it's multiplicative. So for every A, B in A, we want that the valuation of A, B is the valuation of A times the valuation of B. And also it satisfies the strong triangle inequality. The first B is less or equal to the max of the valuations of A and B. So this is what the valuation is. So you see that, okay, a standard choice of target for this map would be, well, you could first of all try to take gamma to be the trivial group, and then you take just a trivial valuation, which sends everything to 1 except 0. But the more interesting choice is the case where you take gamma to be positive real numbers as above, and then terminology is not optimal because then you would maybe be tempted to rather call this minor. But people call this valuation to describe the fact that the target may not necessarily be just a positive real number. We will see later an example where it is. Yes, so this is just what the valuation is, and now I need to write the continuity condition. So you want that for any gamma in gamma, the set of elements in A which satisfy that their valuation is less than gamma is open. So this is the continuity condition. Okay, so here I take strict inequality. In fact, wouldn't make a big difference if I would be taken large inequality, at least if gamma is non-trivial. If gamma is non-trivial, you can always find some element which is strictly smaller than 1, and then by taking powers of this element, you get something which is closer and closer to 0, and so yeah, taking strong or large inequality does not make a big difference. It only makes a difference if gamma is a trivial group, because there you are basically asking that the support of the valuation, so namely the set of elements which are ideal of elements which are mapped to 0 by the valuation, is open, which is non-trivial condition. Okay, and we will say that two steps continuous valuations. Let's say valuation prime are equivalent if well, what you can imagine. So you want that to have an isomorphic, like, okay, so my valuation takes value in gamma, but I can always choose gamma minimal by just looking at the image of the valuation and taking the group which is generated. And this is what I will denote like this here. And what you want is that for these minimal choices of value groups, these two valuations, like there is an isomorphism of two value order abelian groups between the two, it makes a diagram committed. My valuation here this here with this group. Okay. And so now I can explain what is a space we attach to topological space we attach to Hooker pairs. So we define a spar of AA plot to be the set of equivalence classes of continuous evaluations on A with the property that for every x in A plus, the valuation of x is less or equal to 1. Okay, so this is how A plus enters the definition of the associated space. You enforce the condition that elements of A plus have a valuation less than 1, less or equal to 1. Okay, so, but a priori you could say, well, let's forget about A plus and just look at the space of all continuous valuation on A. This is also a natural choice to do, but it will become important to have added this extra parameter later where we try to define study the underlying topological space and the structure of people. Okay, but I did not say this is just a set. So far, on the topology is generated by opens of the form X or some elements F and G in A. So what is this notation? So standard notation, if X is a valuation, continuous valuation on my Hooker ring, instead of writing, and if F is an element of A, well, instead of writing X of F, we will write, because this is more subjective, we will use this notation. So this is what this notation here and here means. Right? So X is a point of this adic space, so its evaluation on A, and I want that its evaluation on F is less or equal to its evaluation of D, which is also required to be non-zero. So you see the basic opens I choose. So like in algebraic geometry, you want to be able to say that something is non-zero, but you also want to be able to allow opens which tell you that something is smaller than something else.
Here, that this is a small step.
But this is
A small step.
no.
I mean, it's other functions. Yeah, but gamma can be in a set. But maybe you can assume that gamma has abnormality then I need to.
Yes, probably. I can think about it, but on the spot.
Gamma is just
The gamma is the choice, the value group of my valuations. I'm looking at all possible valuations.
all possible gamma.
Yeah. So yeah, theory can imagine that very well. Many possible gamma. Yeah. Yes. So the value of has cardinality which must be bounded by. Yes. So there if if I don't put these equivalence relations, it's maybe not small. Yeah. Not even, yeah.
Well, that's for F and G, and for all.
Yes, for all F and G.
No, this open set is parametric. What, because in this basic.
Sorry. Yeah. For some, like the open, I fix F and G in A, and I look at. Yeah. Okay. Sorry. This is I don't like it. So I don't really let me put G, to indicate that it depends on subjects. So Huber proved that this topological space is spectral, which means well, one possible characterization of spectral spaces is that they are either homeomorphic to the spectrum of a ring. There exists a ring such that topological space X is spectral. Means that there exists a certain commutative ring R, so that X has is homeomorphic to the of R. There are other characterizations. Like in particular, it implies that it is quasi-compact. You can also describe spectral spaces as quasi-compact topological spaces with the basis of quasi-compact open neighborhoods, opens, and so that each irreducible closed subset has a unique generic. But in practice, of course, this characterization is, I mean, it's not useful, right? It's just an abstract statement.
But why did you want that to that definition? Why not just smaller? Because you wanted to open. No, it's not open. This is open.
Yeah, I agree. It's a bit fun. But what should be, like, for example, this closed unit ball, I mean, this A, so associated for this vector A, which is up there, the associated and A plus, which is just the same thing with K replaced by K naught. This is the example I will discuss next. It's what would be something to call the closed unit ball, closed because it's defined as inequality that something less or equal to 1. But this could be considered as open. No, because here you are just thinking about like the points in say k to the n for some fixed non-Archimedean field k, which is endowed with this totally disconnected topology, where indeed closed are both closed and open. But here we will be doing topology inside this adic space, or topology defining this way. There, the behavior will be topological behavior will be used.
No, it's a question. We can finite this because otherwise the union of these things is not open. Or you just.
Why do you?
No. Okay. So you can define it this way.
Yeah, that's definition. Yeah, it's not. Yeah,
Just the L and G and F are not continuous.
F and
so the image of open is not open.
I mean, these are elements of A, F and G, and this will correspond. A will be on these adic spaces. A will be the space of global section of the structure sheet. So it should be sort of as A should be sort of.
But they don't seem to be continuous, right? That was the question.
They are continuous between two adic spaces because they will both be. I mean, the image will also be.
What do you mean by continuous here?
Continuous should be continuous. You want to think of it as some kind of continuous section.
Not well.
Apologies.
not really. In the same way as when you do algebraic geometry, you take any commutative ring, you define its spec, and then global sections of the structure sheaf on spec A are just A again.
With values,
I mean,
No, I mean, you just define the structures.
yeah, you define the structures. Right. Yeah, okay. No, sorry.
I will come to examples, and maybe this will clarify the picture. Okay, so this space has this property, and another remark I can make, maybe remark.
So, no finite force spectral.
Sorry, say it again.
It's spectral also means like flow finite force, the inverse limit of finite forces.
Yeah, I think there is also such a characterization. Right. Yeah, there are various equivalent characterizations. So there is a continuous map. I from star AA plus to the spec of A. Well, I just forget the topological structure on A and see it as a ring, commutative ring. Which what it does is that it sends X to the support of X. So the support of X is a set of all elements which are killed by the valuation. So it's a prime ideal, and this map is continuous just because you check that the continuity. You see that the inverse image by phi of if F is in A, and you look inside spec A at the locus, F does not vanish, dF, and you look at the inverse image by phi, what you get is just, well, you just get the condition that F of X should be non-zero. But if you use the notation I had before this, you can just rewrite it like this. So this map is continuous, and yeah, so you can in some sense try to visualize the Adic spaces attached to a pair AA plus as living over spec A with some fibers which are not single. So first example. The case of Z, where Z just endowed with the discrete topology. So as I said, I won't prove anything, I'm just writing down the description of the point. So I have this continuous map phi. And what are the points of this Adic space, star V? Well, so here we have the generic point on spec V, but also for each prime number P, you have the ideal generated by P. And what you have in the fiber over the generic point, you have something I will denote by eta trivial. I also have something which I call eta P. And here something I will call SP. And I will draw this kind of twisted arrows to indicate that when I write this, I mean that Y belongs to the closure of X. So this is a generic point. Its closure contains all the other points. And this point eta P, its closure contains this point. Yeah, for every. Yes, for every. So this is for every branch.
The P lives in the platform.
Exactly. In other words, its support is just 0. So eta trivial is the trivial variation, which sends everything from 0 to 1. Yeah, it's continuous because Z has a strict topology. Eta t for t prime is the following composition. So you have Z. You can send this to dp. And on ZP, you have the continuous periodic valuation now. So you define eta p as this composition. And SP is what you get by modding out by P. And then using the trivial valuation on SP. So again, it sends every non-zero element of FP to 1. So that's the description of this space, of added space attached to. So you see, it's not even in this case you get something which is different from just users.
Is it not my always subjective?
Is it always subjective? I think so. Yeah. I don't remember that. It's not a very. I mean, it's continuous, but it's not spectral in the sense that the inverse image of something quasi-compact is not quasi-compact. So there is another map to the another scheme, which is the reduction map, which is maybe more useful, but I don't want to look at it. Let me now turn to more interesting example of an added space, which is really something periodic. So let me take P a complete non-Archimedean field. Let's say, for example, maybe I will also assume that it is algebraically closed. For example, you can take CP, or you can take, I don't know. Algebraic closure of this, which is takes a TID completion. And then, okay, notation, I will denote by dxr the set of all elements in K. So if for x in K and R positive real number, non-negative, I will denote by dxr the naive closed unit disk, so just the set of all elements in my field K, which satisfies that in the ball, in the closed disk of radius R around X. So this is for the valuation which defines the topology of K. And similarly, if I put a bullet on top, this means to open one. And I will consider the Uber pair A plus, which we already saw before, but just for simplicity with one variable, K, T, K not. So recall this is if bar is a pseudo-uniformizer of K, I take the ring of polynomials in T with coefficients in K naught. I take the bar periodic completion. This is this guy, and then I invert. If I invert bar pi, I get this. Okay, and in this case, you can explicitly describe again all the points of the adic space to X, which is part AA plus, and to which you should think add the closed unities. Okay, so there are actually 5 types of points which I will list, and then I will draw a picture. First class of points, they are called classical points. So these are the points which are seen in Tate's theory of rigid geometry. Namely, whenever I take X in the ring of integers of K, so it's, in other words, it's some element which satisfies that its absolute value is less or equal to 1. Then I can consider the variation attached to it, which sends f in A to, well, first I can evaluate my f at X. This converges, right? Because, as I said, these are power series whose coefficients go to 0 for the topology of K when the exponent goes to infinity. And X has bounded, the powers of X are all absolute value less than 1 in particular. They are power bounded. And the series for non-Archimedean topology converges if and only if its general term goes to 0. So this is a well-defined element of K. And then I can just take its absolute value for the absolute value of K. So this is an example of continuous variation attached to any element X in K. So these are some of the obvious ones. If you think to X as a closed unit disk, you want these points to be there. And they actually they are in one-to-one correspondence with the maximal ideals of this ring. So Tate was defining the geometric object attached to A as that is a set of maximal ideas of A with some slightly weird topology. Then we have points of type 2 or 3, which are defined as follows. So fix some element R, real number between 0 and 1, and again, so maybe this variation attached to X, I can call it X zeros. And again, we choose some element X in K naught. And we look at the valuation XR, which sends F to the following. So let me write F. If you want, I can just write it as a power series like this, in center that around X. And what I do is that I send this to the strip on the disk, closed disk of radius R of the absolute value of Fy. Well, because we are in this non-Archimedean world, this is also just the same as the sup of the AN R to the N or N. Okay, so, well, in some sense, point of type 1 are just the case here where R is taken to be 0. And why do I have both 2 and 3? Well, 2 is the case where this R that I choose belongs to the image of to the value group of K. And this is the case where R does not belong to the value group. For example, if K was CP, then you know that the image of the valuations are all rationals power of P. So if R is such an element, it will be the associated point would be of type 2, and if it's not, then I will say that it is of type 3. So, okay. And we have 2 more types of points. So points of type 4 is some slightly strange phenomenon which can not essential, but something which can happen is that such a field K, despite being complete, algebraically closed, may not be what we call spherically complete field. So it can, okay, let me write it. It can happen that
What's the difference between when one of the two points into the other 2 and 3?
so if R belongs to the value group of K, I call this type 2. If not, I call it type 3. Yeah. So topologically, this will make a difference because if R does not belong to the value group of K, if you slightly change the radius R, then this won't change this associated variation. So in the picture I will draw later, these points of type 2 will be the branching points, whereas at points of type 3, nothing happens when you move along. Okay, so people usually call this point for dead end. What can happen is the following: you can take a sequence of T. Well, I mean, here by disk I mean closed disk. I mean something of the form dxr in K, such that di is contained in di. Sorry, di plus 1 is contained in di over I, but the intersection is empty. Okay, it's a bit strong because if the radius of this disk goes to 0, so if they are more very small, then the intersection will be an empty complete. But it can happen that the radius stay bounded above, and the intersection is empty. So this won't happen if the topology is locally compact. But something like CP is not locally compact. CP is an example which is not spherically. This is related to the failure in this functional analysis of the Hahn-Banach theorem. So this is something which can happen. And in this case, you get evaluation by sending F. If you have such a sequence of disks, you just send F to the int of the scoop over Y I. Okay, but you're free to just ignore these examples. You can always enlarge K to make it spherically complete, and then this will just never happen. And the point of type 4 will be special K. Okay, and then last example, maybe the most interesting, which is the difference between Berkovich and Huber's theory, is that again I fix x in K naught on some element between 0 and 1. And I will now take a value group which is not positive real numbers, but something bigger. So you take the product of positive real numbers by copy of C generated by some element gamma, such that with the property that R prime is smaller than gamma, smaller than R, so R is fixed part of the data, and R prime is any positive real number which is strictly less than R. So this element gamma is infinitesimally close to R and smaller, but it's still bigger than all positive real numbers which are strictly smaller than R. So this can happen like this is not a very rigorous way of defining this. What you could do is take the product with the lexicographic order. And then gamma will correspond to something like, yeah, I don't know. You want to take lexicographic order. Maybe you say that S n is smaller than S prime n prime if S is smaller than S prime, or S is S prime and n is strictly smaller than n. And if you take gamma, which then gamma should, okay, that's gamma should be the element which corresponds to something like this, for example. Second, the formal definition doesn't matter. What matters is this property of gamma, and then what you can do is look at x less than r, which is the valuation again, which sends f. The power series centered of x as the sup in fact, it does not really depend. It only depends on the disk, the open, the open disk. Not like precise choice of x does not really matter. What really matters is this open disk. And similarly, you could define something called x strictly bigger than r, which only depends on, this time it will only depend on the closest center that x is reduced on. And how do you do it? Well, take the same kind of definition, except that you require that gamma is strictly bigger than r, but strictly smaller than all real numbers bigger than. So be careful that, okay, so these are examples of elements of my added space, A plus, but note that you have to exclude one point, namely, if strictly bigger than 1 does not belong to my photo. Because t, for this valuation, the absolute value of t, if I write my convention, if I write this, well, gamma. So this will be strictly, this will be an element strictly bigger than 1. So I break this assumption that on A plus, I only consider continuous variations which are bounded less or equal to 1 on A plus. So this is excluded. But all the other points I just defined, this assumption they belong to this. One more remark is that in this setting, all points of the static space are closed, actually, except the type 2 points. So these points attached to a disk with a rational, like with whose radius belongs to the value group. For type 2 points, the closure of the type 2 points is formed by type 5 points around. So this exotic point, which corresponds to absolute, like to valuations of higher rank. And this closure is in this case isomorphic to P1 over K, where K is the residual field of my non-Archimedean field K, except for the Gauss point, which is x1, because for x1, this would belong, if I would look at this, let's say inside just not the closed ball, but affine space, it would belong to its closure, but this is excluded from it. So which has closure isomorphic to just affine line. So I just have to remove one point from P1. So what are the Gauss points? The Gauss point, there is one Gauss point, which is x1, using this notation I had before. Sorry, x, I have to specify 0. But does not matter, in fact. So it's the evaluation which just sent a power series to its supremum norm on the closed disk of radius 1.
So that's the type 2, 3.
No, there is one Gauss point, which is just the one where the radius is maximum.
Also, this is similarly defined. Can you say what that means?
Okay, so that means that I choose, so this time the value book is again something with this form, but this time I require that gamma has a property that for all r prime real number which is bigger than r, I want to have. So it's a symmetric situation. So the picture is something like this. If you try to represent, to picture this topological space, what does it look like? Yeah.
This Gauss point is supposed to be part of point 3.
It's a point of type 2. Yeah.
But just like it should be in the definition itself, because R was supposed to be less than 1.
I'm sorry. Yeah, okay, that's it. Yeah. Is it good? Yeah. So the picture is something like this. It looks like a tree. So we have the Gauss point on top. And then you have somehow P, like P is 2, so you have P branches starting from it, and then you have some points of type 3, and then you have branches. Something like this. Sometimes, okay, and continues indefinitely until here you have a cloud of classical points. So when you move the radius, go from 1 to 0. R starts with 1 and goes to 0. So these are the type 1 points, the classical points. So it's just something corresponds to points of in K0, so it's like the totality connected thing, which you see below. And there you have, okay, so you have this somewhere, this dead end, this type 4 points, but yeah, let's just forget them. They are not very important. The rest of the picture is formed by this type 2, 3, or 5 points. So the branching points are these type 2 points. And here you see type 3 points on the branches. And what happens if you zoom around the type 2 point? Zoom. What do you see? Well, you see this. These are, as I said, the type 2 points are the only ones which are not closed. So that's why I draw them at points. What you see is you have these branches, P plus 1 branches starting from the point, and if, like in the closure, what? Sorry, no, sorry, no P. Yeah, you're right. Like the point is to make a meaningful picture, I somehow if the residual field will be infinite, right? Because K is algebraic. So, but I just pretend that it's a finite residual field of cardinality Q, say, and then I have Q plus 1 branches around each point of type 2. Otherwise, I cannot really draw any picture. So you see this, like P1 of K, for example, would be hard to. I mean, what you have is something like this. Is that here you have around this, so this is the type 2 point. And in the closure, you have this type 5 point. Except for the Gauss point, where you have to remove the type 5 points which are go in this vertical direction, which corresponds to x strictly bigger than 1.
I didn't really get it, so you said the condition that KD are correctly closed. And just, again, you say that the residue field is finite, but it's only finite.
No, I meant that if the field is algebraically closed, the residual field will be like infinite, and so I cannot really represent the picture because I would have like many branches around each point. Right. So just to simplify, I just pretend that there are finitely many branches around type 2 points.
So this is not the real picture.
So, yeah, the picture is not.
Why do you assume that case of in what condition does
Well, I guess if you want really to get complete descriptions of the points, to have them all of this form, you have to assume the field. Otherwise, you may be missing some points. Yeah, you get like increasing like doing some finite field extensions of the base.
The type of type 5 points. How do we understand each other?
Say it again.
So type 5 points, the type 4. We know at the top. Right?
Yes. Well, yeah. Right.
How do we understand?
Yes, you see, like it's like the how to say that? If I have a type 2 points which would correspond to a disk like this for some x between R, then I have a type 5 points which here, let's say, which corresponds to x strictly bigger than R. But then when you let the radius strictly decrease, so R becomes strictly smaller, then you have various how to say let me like it's like if you take, I don't know, in 2D, for example, if you take the distance of the 0 of radius 1, you can write it as you have the open disk centered at 0 of radius 1, but then you also have like the open disk corresponding to all other elements how to say, so for each in the residual field, I can look at, say I take a lift, so I take some element in K0 which lifts this element of the residual field, and I look at the disk, open disk of radius 1 centered at this point. Right? I mean, they all, yeah. So these are all the elements inside K0 which map this open disk is just a set of all elements in K0 which map this residual class. So you see that. Yeah, sorry, no, but I'm just writing this. I don't know why. Let me just write. Yeah. So you see, and so here this means that. So here I have this type 2 points, which with a strictly bigger condition. But the other point of type 5 that you see around this type 2 points are the ones which correspond to this element. So you also have all the elements like the variant with the radius R, where X runs over the radius. it's really clear what I'm trying to explain.
You also have x that
you also have x less than r. Yes. X, wait, so you say yeah, so that could just correspond to one of them which has the same image as x in the radical. So in this case where x was 0, this is the case where I take x tilde to be 0. I can come back to this. But you see the structure, like looks like, yeah, that's why it has homomorphic to P1 or K. You have all these rational points, isomorphic to rational points of finite. You have this point at infinity, and then you have generic. Except again for this Gauss point where you have element. Something you okay. Let me continue maybe because so I want to make a few remarks about this equation. First remark is that you see that from the description, if you believe in it, that the full dimension is 1. Full dimension is maximal length of specializations of points. We saw that all points are closed except type 2 where you can specialize a type 5 point, and then you stop. So this is quite reasonable. Another thing you should note is, okay, let's consider U inside X. So it is again this closed unity to be the set of all elements that all X such that absolute value of this coordinate T is 1. This is open. Okay, so sorry for complex intuition, but why is it open? Because I can just rewrite it as for you if you want. 1 is always 0, right? With the absolute value of 1. The intersection with X such that so this is an example of the kind of open that below. And then we also look at V, which is the union over all positive epsilons, let's say less than 1, of the disk, of the set of valuations, such that Tx is less or equal to 1 minus epsilon. This is also open because it's the union of open. So here you may be confused because you think, okay, if it knows the union of U and V, which are both open on this curve. So X is disconnected, which is not nice. We wanted to, I was claiming that we were trying to avoid those issues with disconnectedness in non-Archimedean world. And it seems that this does not work, but we are saved by the higher report. Namely, contrary to what one can infer, X is not the same as the union of U and V, because the point, let's say 0, 1, does not belong to the right. Yeah, precisely because for this point, it sends, let me record that this point has a property that the absolute value of T for it is some element gamma, which satisfies that gamma is switched between 1, strictly on R prime for all real number R prime less than 1. So it does not belong to Z, because gamma is always bigger than 1 minus epsilon for all its class. But it also does not belong to you, because gamma is small. So this is really a great feature actually of Hubert series, higher envelopes. In Hubert's theory, you look at all continuous valuations, but valued in R in positive real numbers. Then topology is defined differently. But here it's really nice because we have no, so in fact, X is indeed connected, and we have a nice topological space. Maybe slightly weird, but like I don't expect our rings are slightly weird, but it has good features, contrary to what happens in Tate's theory of Phillips spaces. Okay. I also wanted to make a general remark about specialization of points in Hadith spaces. So when does a point X specializes to Y? Another point, namely when does Y belongs to the closure of X? If you think in terms of evaluations, in fact, these specialization relations are in some precise sense, they are all obtained from the following two constructions. So, first phenomenon is what I will call, so there are two cases, I claim. One is what I will call vertical generalizations. So, yeah. And this is what I will call horizontal specialization. To make the terminology clear, I say that if I have 2 points of Hadith space, star A plus, I say that X, if X specializes to Y, I say that X is a generalization of Y, and conversely, Y into specialization of X. So let's say I start with some variation X, continuous variation, and here is a recipe to produce some generalizations of X. So if you fix H in gamma, then you can do a subgroup, you can do the following. You can look at, construct a new variation as follows. So notation is X over H. Namely, what you do is, so it goes now from gamma over H to union 0, and it sends F to, it depends on whether, so if F of X is non-zero, you send this to Fx mod H is non-zero, and 0 otherwise. Okay, of course, if I take any subgroup H, this may not be again a totally ordered abelian group, so you have to put some condition in H. Namely, in this case, we want this to be convex, I think. I mean, you just have to sit down and see what is the precise condition you want to put on H, so that this is this again defines the continuous valuation. Just to give you an idea of how to produce valuations, new valuations from a given valuation, and such that I claim that this is a generalization of X, if it makes sense. And other recipe is again you have X, And what you can do is following. So again, it's a subgroup with some conditions I won't specify, which ensure that the construction makes sense. And you define its H.
You're not saying that X3 should always be a generalization of X, right? Because I mean, X could be a non-type 2 point and then it doesn't have.
Okay, now I'm back to the general setting of any Uber pair, AA plus. I'm claiming that when this element makes sense, it's a generalization of X.
So you're saying that in the example we have for say.
It's the same.
Well, for type 2 points, you can't do much, right? Because the value group is positive real numbers. So I guess you could just, I guess there will be no possible choice of convex subgroup. Okay, and so other type of relation is that you do that. So now you will send f to f of x if x, so if f of x belongs to H, and otherwise you just kill it. Why do I call this horizontal and vertical specializations? It's because if I remember this map phi from spec A, sorry, from spot AA plus to spec A, vertical generalizations are generalization, specialization relations that only occur in a fiber of phi over a given. So I'm not changing the support of the valuation. These horizontal relations, they are like changing the support. So examples like e.g. In the examples of where A plus is C over D. The first example we had, the eta trivial specializing to eta t was an example of vertical generalizations or specifications, if you like. Whereas eta t going to ST was on horizontal. And important to remark is that if A is tailed, with AA plus is a tailed pair, all specialization relations something one can prove come from a vertical specialization. So the second phenomenon never occurs because somehow what you, like for points of adic space attached to a tailed pair, the support is evaluation, continued evaluation is always non-open, and you can check that if you start with if you use the second recipe, this horizontal specialization construction, if you are really doing something, so if you don't take H to be just gamma, then in fact you will produce a new valuation which has the property that it's kernel, so its support is open. So it won't, cannot happen.
So it's good that says that I can get from one to another one by vertically and then horizontally specified in the sense, how complicated can the specializations be if you say obtained by model construction?
I'm not sure this can be commute really, but yeah, I think the precise statement is that you can either do first vertical and horizontal or the other way around. You get I think you don't have to worry too many things. Okay, so and so in particular, something interesting happens that I want to point it out, because I said at the beginning that as a topological space, A plus is always spectral, so it's isomorphic to the spectrum of a ring. But this result is, I mean, this interpretation is useless. You could not imagine that adic spaces, in general, these topological spaces, they look like, I mean, they behave like what you would expect from schemes. They are abstractly isomorphic to spec of something, but it's spec of a very weird ring. Like you see already in this examples that, yeah, and there are many generic points. So, and in particular, this is illustrated by this fact. So, Tate is really the opposite situation to the discrete or formal scheme situation, because, in fact, from this you can deduce that specialization, like generalizations of the point, so first of all, the point in the Tate case, so another way to think about it, maybe for intuitive reasons, is that you can also just think to it as a morphism with the same thing as a map, spark AK plus, spark AA plus, for some complete non-Archimedean field. Not necessarily a this is in the case of the yeah, this is in the Tate. So for this remark, A is assumed. Okay. Well, okay, there is first condition that the induced map from A to K should have properties of A generates a dense subfield of K. But so if you think in these terms, X corresponds to such a non-Archimedean field, then what, if you want to produce a generalizations of X, what you have to do, well, let me finish in sentence maybe first, generalization of a point form a totally ordered chain. Just looks something like this. You have specializations. You have your given point X, and its generalizations are just yeah. So in terms of this field value descriptions of points, it means that if so X corresponds to Z, then to get the generalizations of X, what you do is just that you can't keep the X and use another yeah, okay. So so if somehow we correspond to this, and I have Y which corresponds to a point which corresponds to morphism from another non-Archimedean field going to spark AA plus. Again, L complete Archimedean field. And assume that Y, or maybe the other way around, but crystallizes to Y. Then, in terms of non-Archimedean fields, this is the same as saying that K and L are the same, and K plus is contained in the wait. So K, no, the other way around. L plus is contained in K plus, which is always contained in four-bounded elements. Okay, so what you are doing is you are just keeping the residue, like this is like the residue field in network geometry. You are keeping the residue field fixed, and you are moving this other parameter. So here again, you see the importance of this, or maybe for the first time, of the this thing. And what happens is that moving along this chain of specialization, you are each time somehow increasing the rank of the value group by 1. So that's what we saw in this one-dimensional case of the closed disk, where it was one-dimensional. So the chain we had was just 2 points. Type 2, the most generic point where the value group is small, it's just positive real number. Then to go to this specialization, this type 5 point, you increase the rank of the value group by adding this factor. Yes, and so, okay, this is if you think about it, it's a behavior which is very different from schemes, right? If you think to any variety of dimension strictly bigger than 1, I don't know, 2-dimensional affine space, take a point and look at its generalization. There are many of them because there are infinitely many electricity components. I mean, there are many. Affine plane, you take a point and you can draw all possible lines to this point. Each of these lines has a generic point. There are no specialization relations between these various things. So, yeah, but that's a very different behavior from scheme this time. Okay, now I'm out of time officially, I think. So take a little more. Yeah. I will try to shorten it.
What's the overall plan?
Now I want to, okay, so you see, I just discussed this topological space attached to a Huber pair, but not yet. I want to get in the end a locally unique space. So I still have to define the structure shift. Yeah, then I wanted to end with some more examples, including the far content curve. This is better examples. I keep them for next time. So maybe I can just briefly say how we define and then stop. Yes. Okay. So for this, I need one more definition. So notation. If you have S in A and T a finite subset of elements which satisfy that such that idea generated by T in A is open, then let me define U and call this a rational subset. That's terminology. So it will live inside X, which is so I'm going to say A plus pair, which is defined to be the subspace of elements in X which satisfies that T of X is smaller than S of X, all, and this is different from 0 for all T in T. So T is finite. So it's open, right? Because it's intersection of many basic opens. And why do I give them a special name? It's because of the following result of Huber. Very important statements that if U is inside X is a rational open, then there exists complete Huber pair, which is denoted, which lives over AA plus and is successively denoted OX of U, OX plus of U. So this is my Huber pair. It's just notation so far. With the property that star OX U, OX plus U. So functor spa is contravariant, so it maps to it, right? And claim is that it factors over U. Is universal with this property. And in fact, even better, it induces homeomorphism in this accumulated space for x u or x plus u, and this space. Okay, so I have such a Huber pair attached to a rational subset, so that in fact U is described as spa of this pair, and it almost a universal choice in the sense that if I have any other Huber pair BB plus over AA plus, so that spa BB plus has image in U, it must receive the map from this Huber. Okay, and here it's really, I won't prove it, but let me just point out that like if something like this, you have a pair BB plus, so that spa BB over AA plus, so that spa BB plus maps to U. Then okay, so one just thing I want to stress is that this works well because of this assumption that it would not work for a random basic open as defined at the beginning when we define the topology. It works well because we put this condition that A in A is broken. For example, let's imagine that you would, I don't know, you would take, like in fact, if you want to OXU, it will be defined as as A 1 over S completed for the I comma A naught T over S T1 over S blah blah TD over S endowed with yeah, that formulation is not extremely precise. What I mean is the following: you look at A and you just invert S, and then okay, inside it, choose a ring of definition A naught, some ideal of definition I, finitely generated. Then you look at A naught 1 over S, and you will undo it with like a ring of definition for this guy will be just this thing with topology corresponding to the idea generated by I inside. And then you take the completion. You need to take the completion if you want the universal property to have a chance to be true. You take the completion of this. Yes. No, I'm. Yes. Very good. And so, okay, then the claim is that this will be a Huber ring. The verification that it is a Huber ring will crucially use the assumption about T that we have. For example, if you would take A, this dP double bracket T with the PTL topology, a kind of topological ring one works within formal geometry, you cannot like A and say you want to, I don't know, imagine that you take T to be T, for example. So, because, yeah, okay, so X. Just to this is not open, right? Because the idea something is open if and only if it contains the power of this idea, maximum idea P. And you can check that there is no way to make this A1 over P a topological ring such that A inside it is endowed with the P-ecladic topology. Like, because you want multiplication by 1 over P to be continuous, but if you take, I don't know, 1 over P to the T to the N, to the X to the N, this will never converge to 0 because it never enters this subring A. Something to think about because my explanation is quick, but definition 1 minute. We have this important theorem. In particular, you see that it implies that any rational subset is spectral again because it's part of something. As a corollary, a rational subsets R over R with a compact, even spectral. But be careful that but not general basic opens as if FG that we have. If you can think about why. And so now that we have we define this W, this X is open, you define O plus X, so OX of U and also O plus X of U. Yes, thanks. And the inverse limit over all possible choice of rational subset containing W, in W of OX of U. OX of U is defined as the same thing for this positive structure shift. Okay, and this is sheaf of rings on this topological space spa A plus, and then in general adic spaces will be glued, will be exactly like locally ring spaces plus conditions which can be glued from these affine pieces, this spa A plus. One has there are some subtleties in the theory, like this is not this OX is not a sheaf in general, so it's not a free sheaf. And then, well, you are a bit stuck if it's not a sheaf. But I will largely ignore this issue, simply because in all practical situations, like any spaces, study them or perfect spaces or schemes or formal schemes, it is always a sheaf. First, and then also because I think the fact that it's not a sheaf is not. I think I forgot the names, but at least Clausen-Schulze, in the more general formalism, if you take everything derived, somehow this issue disappears. So it's really just related to the fact that in the classical theory, we always work on derived. Problems may happen. Topological issue may come up. There are some actual examples where this definition does not give rise to a shift, but as I said, in practice, we can just forget about it. Always. Sorry? No, so this W is not part of something. It's just an open inside my X was again. Sorry. X is by plus one of inverter, and then I take just any open inside this. But it may not be
the regular subsets are doing other basis.
yes.
And then this is just the way you always.
Exactly. Yes. It's just that when we, I mean, that's
maybe I'm asking what is the role of OX plus W? If they of written for the basic rational, this is sort of the part of that I need to look at. If OXW and OX plus W is not a good answer, what's the role of the OX plus?
Well,
if you say it's a sheaf of rings, then you need OX.
Well, it should be sort of a sheaf of topological rings, I guess, but I mean, I don't know, it's just convenient to have it. Like, for example, you can then define the local ring at a point, as you would do, and you can also define the first version inside this. When you go to this will be a local ring, you can take a residual field, which will be again a value field, and this will ultimately define the valuation ring, which is exactly the kind of thing I used above to describe the specialization relation. So I don't know, you just want to remember this information of this problem. But you can completely recover plus X inside OX as elements which have like valuations less or equal to 1. This is actually. And in some arguments, I don't know, in the state setting, you go from this one to this one by inverting the two uniformizer. You may do some derivative to prove some properties to reduce to O plus, which you can then reduce, modify. Okay. This is, for example, what one constantly does in the serial space.
So what? So why does it not work there? I mean, where does it fail? I sort of think of it as the same properties.
Well, it may not even be, I don't know, again, in the Tate setting, it may not even be, in the Tate setting, the Tate ring over some non-Archimedean field is, in particular, a banner at the border. Okay. Right? Basically because of general description of them, I get that you always get them by using some closed ball and then but this may not in general be a banner scale at the moment. You take a limit. Imagine that you are looking, for example, at something which is like, I don't know, an increasing union of balls, like open space, and then you take global section, and you are taking an inverse limit of banner algebra, so it's just a pressure algebra. So it won't be taken. Thanks. Will we stop? I don't know which one I should.